Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The continent of Antarctica holds more than 90% of Earth's ice, a frozen desert that has concealed its secrets for millennia. But beneath this seemingly static landscape lies a dynamic world that scientists are only beginning to understand. A network of flowing freshwater rivers that course beneath the ice sheets, hidden from human eyes until recent decades. These subglacial waterways represent one of the last great frontiers of terrestrial exploration on our planet. In the perpetual darkness, under ice sheets that can be more than 2 kilometers thick, water flows in channels and streams, carving pathways through bedrock and sediment. These aren't merely trickles, but vast systems. Some subglacial Antarctic rivers stretch for hundreds of kilometers, carrying volumes of water comparable to some of the world's major rivers. The discovery of these hidden hydrological systems has revolutionized our understanding of the southernmost continent. The scientific journey to discover Antarctica's subglacial rivers began in earnest in the 1970s, when researchers first theorized that liquid water could exist beneath the crushing weight of the ice sheets. The pressure from above lowers the freezing point of water, while geothermal heat from below provides the energy needed to maintain liquid conditions. This delicate balance creates a hidden hydrosphere that remained largely theoretical until the 21st century. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe, it's free, and it helps us grow this community together. The first definitive evidence of subglacial water appeared in the form of a lake, not a river. In 1996, Russian scientists confirmed the existence of Lake Vostok, a massive freshwater lake the size of Lake Ontario, buried beneath 3.7 kilometers of ice. This discovery transformed glaciology, demonstrating that large bodies of liquid water could indeed exist in the extreme environment beneath Antarctica's frozen surface. But the dynamic nature of Antarctica's subglacial hydrology wasn't fully appreciated until the early 2000s, when satellite observations began to reveal something unexpected. The ice surface of Antarctica wasn't static. It was rising and falling in certain regions, by as much as 10 meters over periods of months to years. These vertical displacements could only be explained by water movement beneath the ice, filling and draining massive subglacial reservoirs. In 2007, a team led by glaciologist Helen Amanda Fricker of the Scripps Institution of Oceanography made a breakthrough discovery. Using data from NASA's Ice Cloud and Land Elevation satellite IceSat, Fricker and her colleagues identified active subglacial lakes beneath the Whillans ice stream in West Antarctica. More importantly, they observed these lakes filling and draining in sequence, direct evidence of water flowing between them in subglacial rivers. The following years brought rapid advances in technology that allowed scientists to peer beneath the ice with unprecedented clarity. Radio echo sounding, similar to the technology used in medical ultrasounds, enabled researchers to map the bedrock beneath Antarctica and identify the channels where water might flow. Meanwhile, satellite instruments like IceSat-2, launched in 2018, tracked subtle changes in ice surface elevation with centimeter-scale precision, revealing the dynamic movement of water below. By the early 2020s, scientists had identified more than 400 subglacial lakes across Antarctica, connected by an extensive network of rivers and channels. These waterways don't just exist, they're fundamental to the continent's glacial dynamics, acting as lubricants that influence how rapidly ice flows toward the ocean. Understanding these hidden rivers has become crucial not just for basic science, but for predicting how Antarctica will respond to our warming climate. The very existence of liquid water beneath kilometers of ice seems to defy intuition. How can rivers flow in an environment where temperatures routinely plunge to minus 55 degrees Celsius at the surface? The answer lies in the extraordinary physics of pressure, geothermal energy, and friction that create a hidden hydrological system unlike any other on Earth. Water beneath the Antarctic ice sheets exists in a state of delicate thermodynamic balance. The tremendous weight of the overlying ice, which can exceed 4,000 meters in thickness, exerts pressure that lowers water's freezing point through a phenomenon known as pressure melting. For every 100 meters of ice, the melting point decreases by approximately 0.7 degrees Celsius. Under 2 kilometers of ice, water remains liquid even at temperatures several degrees below 0 Celsius. This pressure effect creates the potential for liquid water, but it's the heat from below that provides the energy to maintain this state. Antarctica's bedrock emits geothermal heat at rates that vary across the continent, from 20 to 200 milliwatts per square meter. While these values seem tiny compared to the cold of Antarctica's surface, they represent a significant and constant energy input at the base of the ice sheet. Additional heat comes from friction. As massive glaciers and ice streams slide over the bedrock below, the friction generated contributes heat to the system. In the most active ice streams, this frictional heating can exceed the geothermal heat flux, doubling the energy available to melt ice. The faster the ice moves, the more heat it generates, creating a feedback loop that can accelerate melting and water production. The water in Antarctica's subglacial rivers isn't static. It flows under hydraulic pressure gradients, created by the ice sheet itself. The immense weight of ice creates what glaciologists call the hydraulic potential, essentially, the energy available to move water from one location to another. Unlike surface rivers, which flow downhill following topography, subglacial rivers flow along paths determined primarily by the thickness of the overlying ice, not just the slope of the bedrock. This creates counterintuitive flow patterns. Subglacial water can flow uphill against bedrock slopes if the ice above thins in that direction. The hydraulic potential is approximately 10 times more sensitive to changes in ice thickness than to changes in bed elevation. This phenomenon leads to water routing that would be impossible in any surface river system. The properties of these subglacial rivers differ dramatically from their surface counterparts. Lacking exposure to air, they contain no dissolved oxygen except what was originally trapped in the melting ice. Their dissolved mineral content depends entirely on the bedrock they flow through, creating chemistry unique to each river system. Some subglacial rivers in Antarctica flow through iron-rich sediments, emerging at the ice margin as spectacular blood falls, rust-colored outflows that represent one of the few visible signs of the hidden hydrosphere. The temperature of these rivers hovers just barely above the pressure-adjusted freezing point, typically between -2 and 0 degrees Celsius. Despite these frigid conditions, the water remains liquid due to the immense pressure. The moment these waters emerge from beneath the ice and pressure is released, they can freeze almost instantly in the Antarctic air. Flow velocities in subglacial rivers vary tremendously. In narrow, well-defined channels carved into the bedrock, known as R-channels, water can move at speeds exceeding 1 meter per second during high-flow events. In contrast, water flowing through the thin distributed network of cavities and sediments beneath the ice, called a distributed system, might creep along at mere millimeters per day. These fundamentally different flow regimes, channelized versus distributed, represent one of the most important distinctions in subglacial hydrology. Channelized systems efficiently move water through the subglacial environment, potentially reducing ice sliding speeds by draining water pressure. Distributed systems, by contrast, maintain high water pressure across broader areas, potentially accelerating ice flow through enhanced basal lubrication. To map rivers that flow in perpetual darkness beneath kilometers of ice requires ingenuity and technological innovation. Scientists have developed an impressive arsenal of techniques to detect, measure, and monitor Antarctica's hidden waterways. Overcoming the immense challenges of accessing this remote and hostile environment, radio echo sounding serves as the primary tool for penetrating the ice veil. This technology, similar to ground-penetrating radar, sends radio waves through the ice sheet and records the reflections that bounce back. Different materials, ice, water, and rock, reflect these waves differently, allowing scientists to distinguish between them. Water appears as particularly bright reflectors, creating distinctive signatures that stand out in radar profiles. Since the 1970s, aircraft equipped with radio echo sounding instruments have crisscrossed Antarctica, gradually building, a picture of the continent's subglacial landscape. The British Antarctic Survey's BedMap project and its successor BedMap 2 have compiled these radar soundings into comprehensive maps of Antarctica's bedrock topography. These maps reveal the valleys and depressions where water might accumulate and flow. The latest iteration, BedMap 3, incorporates data from dozens of international surveys and provides the most detailed view yet of the hidden landscape beneath the ice. Satellite observations have revolutionized the study of subglacial hydrology. NASA's Ice Cloud and Land Elevation Satellite, IceSat and IceSat-2, uses laser altimetry to measure the height of the ice surface with remarkable precision, down to a few centimeters. When water moves beneath the ice, it can cause the surface to rise or fall, creating subtle elevation changes that these satellites can detect. By tracking these changes over time, scientists can observe subglacial floods and the filling and draining of lakes in real time. The European Space Agency's CryoSat-2 satellite uses radar altimetry to achieve similar measurements, particularly useful in Antarctica's interior, where optical instruments can be hindered by darkness and cloud cover. Meanwhile, satellites equipped with synthetic aperture radar, SAR, can measure ice velocity, helping scientists identify regions where subglacial water might be lubricating the ice base and accelerating flow. Seismic surveys provide another window into the subglacial environment. By creating small controlled explosions or using mechanical hammers to generate seismic waves, scientists can analyze how these waves travel through the ice and reflect off boundaries below. The distinctive way seismic waves propagate through water allows researchers to confirm the presence of subglacial lakes and estimate their depths. For direct observation, nothing compares to ice drilling. Since the 1990s, several major projects have drilled through the Antarctic ice sheet to access the water below. The Whillans Ice Stream Subglacial Access Research Drilling, WISARD project, successfully penetrated the Whillans Ice Stream in 2013, reaching a subglacial lake system and retrieving water samples. Similarly, the Subglacial Antarctic Lakes Scientific Access SALSA project drilled into Lake Mercer in 2018-19, collecting unprecedented data on the biology, chemistry, and hydrology of a subglacial lake. These drilling projects employ sophisticated technologies to prevent contamination of the pristine subglacial environment. Hot water drills melt a narrow hole through the ice using pressurized heated water that's been filtered and sterilized. The boreholes created are temporary. They begin refreezing immediately after drilling, giving scientists a brief window to deploy instruments and collect samples before the access point closes. Once access is gained, researchers deploy specialized sensors to measure water properties. Conductivity temperature depth, CTD probes, record basic physical parameters, while custom-designed current meters measure flow velocity. Video cameras housed in pressure-resistant casings provide visual confirmation of subglacial conditions, capturing imagery from an environment few humans will ever see directly. Perhaps most ingenious are the autonomous vehicles designed to explore beneath the ice. In 2021, the IceFin robot, a torpedo-shaped autonomous underwater vehicle just slim enough to fit down a 30-centimeter borehole, was deployed beneath the Thwaites Glacier in West Antarctica. Its mission, to travel horizontally through the water-filled cavity between ice and bedrock, mapping the interface and measuring water properties along the way. In the complete darkness beneath Antarctica's ice sheets, where pressure is crushing and temperatures hover just above freezing, scientists have discovered something extraordinary: life. These subglacial waterways aren't sterile conduits of meltwater but living ecosystems, harboring microorganisms that have evolved to thrive in one of Earth's most extreme environments. The first evidence of life in these subglacial systems came from Lake Vostok, where Russian scientists drilled through more than 3.7 kilometers of ice in 2012, after decades of effort. Analysis of water that had frozen to the drill bit revealed microorganisms with DNA sequences distinct from any known surface organisms. These findings suggested something remarkable a subglacial ecosystem potentially isolated from the surface for millions of years. More direct evidence came from the Wizard project at subglacial Lake Whillans in 2013. Using carefully sterilized equipment to prevent contamination, the team retrieved water samples containing approximately 1,000 bacterial cells per milliliter, about 10% of the concentration found in surface oceans, but far higher than expected in such an extreme environment. DNA analysis identified nearly 4,000 distinct bacterial species, many previously unknown to science. The microbes inhabiting these lightless rivers and lakes face extraordinary challenges. Without sunlight, photosynthesis is impossible, removing the primary energy source that powers most of Earth's ecosystems. Instead, these organisms rely on chemosynthesis, deriving energy from chemical reactions involving minerals in the water and sediment. Many are chemolithotrophs, literally rock-eaters, obtaining energy by oxidizing iron, sulfur, or manganese compounds leached from the bedrock. The metabolism of these microorganisms is extraordinarily slow by surface standards. Laboratory studies suggest that subglacial bacteria may divide only once every few months or years, compared to hours or days for their surface relatives. This glacial pace of life is an adaptation to the limited energy available in their environment. Carbon sources for these ecosystems come from multiple origins. Some derives from ancient marine sediments deposited when parts of Antarctica were ocean floor millions of years ago. These organic-rich sediments provide a legacy food source that microbes can slowly metabolize. Other carbon enters the system through meltwater, which can carry tiny amounts of organic matter from the surface. The microbes themselves create additional organic carbon through chemosynthesis, supporting a simple but functional food web. Remarkably, researchers have identified complete nitrogen cycles in these subglacial ecosystems. Different microorganisms specialize in various transformations of nitrogen compounds. Some fix atmospheric nitrogen into forms usable by other life, while others perform nitrification or denitrification. This complex biogeochemical cycling in such an isolated environment demonstrates the resilience and adaptability of microbial life. The discovery of methane in subglacial waters points to another important group of organisms, methanogenic archaea. These ancient microbes produce methane as a metabolic byproduct, contributing to the unique chemistry of the subglacial environment. Other microbes then consume this methane, creating a microbial methane cycle entirely beneath the ice. Beyond bacteria and archaea, scientists have identified more complex organisms in some subglacial waters. The SALSA project's exploration of Lake Mercer in 2018 surprised researchers by discovering the remains of tardigrades, rotifers, and crustaceans, multicellular animals not previously known to inhabit the subglacial environment. While it remains unclear whether these organisms were living in the lake or were preserved remains transported from elsewhere, their presence suggests that subglacial ecosystems may be more complex than previously thought. These subglacial ecosystems may represent the closest Earth analogues to potential habitats on icy moons like Europa and Enceladus, where liquid water oceans exist beneath thick ice crusts. The microorganisms thriving in Antarctica's hidden waterways provide a template for understanding how life might evolve in similarly extreme environments elsewhere in our solar system. The resilience of life in these extreme conditions has profound implications for understanding the limits of habitability on Earth and beyond. If microorganisms can thrive in the cold, dark, high-pressure environment beneath Antarctica's ice sheets, similar life forms might exist in subsurface oceans throughout the solar system, dramatically expanding the potential habitable zone beyond the narrow range traditionally considered. Antarctica's hidden rivers don't merely exist as curiosities beneath the ice. They fundamentally control how the continent's massive ice sheets move and evolve. These waterways function as a dynamic plumbing system that lubricates glacier flow, influences ice stability, and ultimately affects how quickly Antarctica contributes to sea level rise. To understand this relationship, we must first recognize a fundamental glaciological principle. Ice sheets don't simply rest on the bedrock beneath them. they slide. This sliding motion, called basal slip, accounts for a significant portion of how quickly ice moves toward the ocean. In some fast-flowing ice streams, basal slip can contribute up to 90% of the total ice velocity. The presence of water at the icebed interface dramatically enhances this sliding process. As little as a millimeter-thick film of water can reduce friction between ice and bedrock by orders of magnitude, effectively greasing the bottom of the glacier. Where water pressure approaches the weight of the overlying ice, the glacier can become partially buoyant, further accelerating its forward motion. Subglacial rivers regulate this process through a complex relationship between water pressure and ice dynamics. When water spreads out in a thin, distributed layer across the glacier bed, pressure remains high throughout the system, maximizing the lubrication effect. This configuration typically occurs during winter months or in regions where water production is relatively low. By contrast, when water concentrates into efficient channels, R channels carved upward into the ice, or N channels cut downward into the bedrock, it can actually reduce the average water pressure across the glacier bed. These channelized systems act like effective drainage pipes, drawing down water pressure and potentially slowing glacier movement. This configuration typically develops during summer melt seasons or in areas with abundant water supply. The seasonal cycle of glacier acceleration and deceleration, observed in many Antarctic ice streams, directly reflects this shifting subglacial hydrology. As summer meltwater production increases, glaciers initially accelerate when the drainage system is overwhelmed. Later, as channelized drainage develops, the same glaciers may paradoxically slow down despite increased water input. Antarctica's largest ice streams, rivers of ice moving up to several kilometers per year, often coincide with major subglacial water routeways. The Willan's ice stream in West Antarctica, moving at speeds up to 800 meters per year, flows above a network of interconnected subglacial lakes and channels. Recent research suggests that periodic draining of these lakes triggers stick slip motion in the ice stream, causing it to lurch forward in distinct episodes rather than flowing steadily. Subglacial rivers don't just affect ice speed, they influence stability. Where subglacial water freezes to the bottom of a glacier, it can anchor the ice to the bedrock, creating sticky spots that stabilize the entire system. Conversely, where concentrated water flow erodes the bed material, it can create cavities that reduce this anchoring effect. The balance between these processes helps determine whether an ice stream maintains a stable position or retreats inland. Perhaps most concerning for Antarctica's future is the role subglacial rivers play in ice shelf stability. Ice shelves, the floating extensions of land ice that fringe much of Antarctica, buttress the continent's glaciers, slowing their flow into the ocean. Where subglacial rivers emerge at the grounding line, the transition point where land ice begins to float, they can accelerate ice shelf melting from below. Recent studies using autonomous underwater vehicles beneath the Pine Island Glacier ice shelf have observed subglacial rivers continuing their flow under the floating ice, creating channels in the ice shelf's underside. These channels weaken the ice shelf structure and provide pathways for warmer ocean water to access the grounding line, potentially accelerating ice loss. Climate change complicates this picture, as atmospheric warming increases surface melting. On parts of Antarctica, more water may enter the subglacial system, potentially reorganizing the continent's hidden plumbing. Simultaneously, ocean warming increases melting at grounding lines, where subglacial rivers discharge into the sea. The interaction between these processes creates feedback loops that current models struggle to fully capture. Understanding how Antarctica's subglacial rivers control ice dynamics has become crucial for predicting the continent's contribution to future sea level rise. Current models suggest that Antarctica could contribute anywhere from a few centimeters to more than a meter of sea level rise by 2100, with subglacial hydrology representing one of the largest sources of uncertainty in these projections. Beneath Antarctica's ice sheets lie sediments and rocks that have remained undisturbed for millions of years, preserved in the cold, dark environment created by the overlying ice. These sediments, transported and deposited by subglacial rivers, contain an unparalleled archive of Earth's climate history, a record that extends far beyond the 800,000 years captured in ice cores. When subglacial rivers flow, they carry sediment eroded from the bedrock beneath. This material ranges from fine silt particles to coarse gravel, depending on the flow velocity and the nature of the bed material. Where these rivers slow down or enter subglacial lakes, the sediments settle out, creating layered deposits that accumulate over thousands or millions of years. Drilling projects that have penetrated these subglacial sediments have recovered cores containing extraordinary climate records. In 2013, the Antarctic Geological Drilling (ANDRIL) project retrieved a sediment core from beneath the Ross ice shelf that contains a continuous record spanning the past 20 million years. Analysis of these sediments revealed cycles of ice sheet advance and retreat driven by orbital variations in Earth's axis and path around the Sun. Perhaps most remarkable are the microfossils preserved in these sediments. Diatoms, microscopic algae with silica shells, have been found in sediments from Lake Hodgson on the Antarctic Peninsula, which was covered by ice until relatively recently. These diatoms provide evidence of periods when the lake was ice-free and exposed to sunlight, allowing photosynthetic organisms to thrive. Deeper in Antarctica's interior, subglacial Lake Vostok has accumulated over 100 meters of sediment at its bottom. While these sediments remain largely unsampled due to the technical challenges of drilling without contaminating the lake, they likely contain a climate record spanning the entirety of Antarctica's glaciation, potentially 15 million years or more. The chemical composition of subglacial sediments provides another window into past climate conditions. By analyzing the ratios of different oxygen isotopes in minerals formed during different periods, scientists can reconstruct past temperatures with remarkable precision. Similarly, carbon isotopes in organic matter preserved in the sediments reveal information about ancient carbon cycles and atmospheric carbon dioxide levels. Magnetic minerals in subglacial sediments record the orientation of Earth's magnetic field at the time of deposition. These paleomagnetic signatures can be matched to known periods of magnetic field reversal, providing a dating framework for the sedimentary record. Combined with radiometric dating techniques, this allows scientists to establish precise chronologies for climate events recorded in the sediments. Perhaps most valuable for understanding Antarctica's future is the record of past ice sheet collapses preserved in these sediments. During the mid-Pliocene warm period, approximately 3 million years ago, global temperatures were 2 to 3 degrees Celsius warmer than pre-industrial levels, similar to what Earth may experience by the end of this century. Sediment records from this period show that parts of the West Antarctic ice sheet collapsed, raising global sea levels by several meters. Subglacial rivers play a critical role in accessing these ancient archives. Where rivers emerge at the ice margin or discharge into the ocean, they carry sediment from deep within the continental interior. These deposits, known as glacial outwash, provide samples of material from regions that would otherwise be inaccessible without drilling through kilometers of ice. The chemistry of water in subglacial rivers also carries climate information. Dissolved gases trapped in ancient ice are released when that ice melts at the glacier base, entering the subglacial water system. By analyzing water samples collected where these rivers emerge, scientists can measure the compositions of ancient atmospheres preserved in the ice. Advances in genomics have opened another window into the past through environmental DNA preserved in subglacial sediments. Ancient DNA from plants and animals can survive for thousands of years in the cold, oxygen-poor environment beneath the ice. Analysis of this genetic material has revealed evidence of temperate forests that once grew in Antarctica before the continent froze, with tree species related to modern southern beech found in New Zealand and Patagonia. These sedimentary archives provide crucial context for understanding current climate change. They reveal that Antarctica's ice sheets have not always been stable. They have grown and retreated numerous times throughout Earth's history. However, they also show that the current rate of change driven by human activities far exceeds natural variability, emphasizing the unprecedented nature of anthropogenic climate change. By studying how Antarctica's ice sheets responded to past warm periods, scientists can better predict how they might behave in our warming future. The sediments transported by subglacial rivers provide the most complete record available of these past changes, making them invaluable resources for climate science. On the frontiers of Antarctic science, researchers are deploying innovative technologies and methodologies to probe deeper into the continent's hidden waterways. These efforts aren't merely academic, they're crucial for predicting how the frozen continent will respond to our warming climate and, consequently, how quickly sea levels may rise in the coming decades and centuries. One of the most ambitious current projects is subglacial, a European initiative developing an innovative probe capable of drilling through more than 3 kilometers of ice in a single season. Unlike conventional drilling operations that take years to reach subglacial water, subglacial uses a high-pressure hot water drill with integrated scientific instruments. As it descends, it analyzes ice cores in real time, transmitting data to the surface without having to retrieve physical samples. Meanwhile, the International Thwaites Glacier Collaboration, a joint effort between American and British scientists, is conducting the most comprehensive study ever of West Antarctica's most vulnerable glacier. Using a combination of geological mapping, airborne geophysics, and oceanic and glaciological observations, researchers are investigating how subglacial hydrology influences the glacier's acceleration. Their findings suggest that warm ocean water is infiltrating far beneath the glacier along subglacial channels, potentially accelerating its retreat. Artificial intelligence is revolutionizing the analysis of radio echo sounding data. Machine learning algorithms trained to identify the distinctive signatures of subglacial water features can process vast datasets much faster than human analysts. These methods have already identified previously unknown subglacial lakes and river systems. In regions with limited survey coverage, particularly in East Antarctica's highlands, satellite technology continues to advance our understanding of Antarctic hydrology. The Surface Water and Ocean Topography (SWOT) satellite, launched in 2022, can detect surface elevation changes with unprecedented precision. Combined with ICSat-2 data, these observations allow scientists to monitor the movement of water beneath the ice in near real time, tracking flood events as they propagate through the subglacial system. In the biological realm, researchers are using environmental DNA techniques to study the biodiversity of subglacial ecosystems without direct sampling. Water collected where subglacial rivers emerge at the ice margin contains DNA fragments from organisms living throughout the subglacial watershed. By sequencing this genetic material, scientists can catalog the microbial communities without drilling into pristine subglacial environments. Improvements in ice sheet modeling represent perhaps the most crucial frontier for understanding Antarctica's future. The latest generation of models incorporates subglacial hydrology in increasingly sophisticated ways, simulating how water pressure affects ice sliding and how river networks evolve over time. These models suggest that changes in subglacial drainage patterns could either accelerate or mitigate ice loss, depending on complex feedback mechanisms. Climate projections for Antarctica remain uncertain, with estimates of sea level contribution by 2100 ranging from 20 centimeters to over 2 meters. Much of this uncertainty stems from our incomplete understanding of subglacial processes. As models improve incorporating new observations of subglacial hydrology, these projections will become more precise, allowing coastal communities worldwide to plan more effectively for future sea level rise. Beyond Earth science, Antarctic subglacial research has implications for astrobiology. NASA's Europa Clipper mission, scheduled to launch in 2024, will study Jupiter's icy moon Europa, which harbors a global ocean beneath its frozen surface. The technologies and methodologies developed to study Antarctic subglacial environments serve as test beds for future space missions that might sample these extraterrestrial oceans. The ethical dimensions of subglacial exploration continue to evolve. The Scientific Committee on Antarctic Research has established stringent protocols for accessing subglacial environments, balancing scientific discovery with environmental protection. These guidelines ensure that exploration doesn't contaminate pristine ecosystems that have evolved in isolation for millions of years. Looking ahead, the next decade promises transformative discoveries in Antarctic subglacial science. Plans are underway for the first comprehensive mapping of Antarctica's entire subglacial hydrological system, combining airborne surveys with satellite observations and ground-based measurements. This effort will provide the first complete picture of how water moves beneath the ice sheet, essential knowledge for predicting its future behavior. As technology advances and international collaboration intensifies, our understanding of Antarctica's hidden waterways grows exponentially. Each discovery reveals not just the complexity of Earth's southernmost continent, but also its vulnerability to human-induced climate change. The rivers flowing in darkness beneath Antarctica's ice carry not only water and sediment, but also crucial information about our planet's past and warnings about its future.